Hello everyone, welcome to Tech with Machines. Today we are back with one of the topics which we discussed earlier, distributed locking strategies. We will go through real world example. We'll also talk about the trade-offs of each of the strategies, or basically how to classify those strategies, as well as when not to use locks. Now, if you have ever used Redis locks, ZooKeeper, or heard about Redlock, this video will connect all the dots. So let's first talk about the basic what distributed locking really means. And if you want to, I'll just give a quick overview of it. If you want a detailed overview, then you can actually go through my previous video. Now, the fundamental problem is the same, that let's say there is a payment DB and there are 5 microservices which are actually trying to access that shared DB. And if they are trying to update the same payment record, possibly you will get charged twice. There could be inconsistent updates and it will lead to corruption. So this basically is nothing but a race condition. So in this case, we actually need mutual exclusion. Now, we could have thought about local lock like mutex, but when it comes to distributed, there is no shared memory. There is no central authority. So locking is basically becoming a coordination problem. So we can say that distributed locking is equal to coordination under failure. So it is coordination, failure handling, and correctness. Now, implementing distributed locking is hard because we can have clock drift, or if a server crashes while holding a lock, who can release it? Who will release it? Or if a network partition happens, you might have to determine who is owning the lock. Or if a GC pause freezes a process for 20 seconds, is it still the owner? This is where things get a little complicated and dangerous. That's why we have multiple locking strategies, and there is a common classification which helps to define them. One, where the source of truth lives, because it's a distributed locking, so who owns the lock? And in case of failure, how they are handled, as well as how we will ensure there is no stale writes or there is data correctness. Let's start with the first locking strategy, which is centralized locking strategy. It's a simplest approach. What does it mean? It means use a central store. Use a system which can grant the lock, like database locks or a single Redis instance. This is very simple and it works when there are low traffic workloads. Basically, the performance is not critical, or you want to have multiple cron jobs running and have a coordination among them. So in this case, a basic implementation is that you are setting the lock or owning or granting the lock. So like in case of Redis, you are saying set the lock key if doesn't exist. So you will get the lock acquiring is successful. If it exists already, then you are retrying. So most of the production systems use this because it's very simple and it is suitable for systems which doesn't have a critical performance. But it does have its pros and cons. So as we spoke, that it gives a strong consistency, it's very simple to implement, as well as it has minimal operational complexity. But at the same point of time, it also has its own drawbacks, comes with its own share of failures, like it becomes a single point of failure. And if there is high traffic, then it becomes a bottleneck. There is no automatic cleanup of locks, so the locks can't recover. If there is a crash, you can't really recover from the lock. So it does work, but it's fragile in terms of concept. So to overcome its limitation, there is another strategy called lease-based locking strategy. You basically are acquiring or getting a lease in terms of TTL. So in this also, you acquire a lock key, but this time with an expiry, so that you can avoid permanent deadlocks. But does this enforce correctness, or does this enforce that stale writes won't happen? No. It ensures that if your node crashes, you are able to recover from it and you don't go into a permanent deadlock kind of a situation. Now in this case, lock is expiring automatically, and X stands for if the lock key doesn't exist, then acquire it. And EX here stands for the expiry, so expire after 30 seconds. So, but let's say hidden danger, what is there? That it relies on time assumptions, right? Now let's say node A has acquired a lock, or server A has acquired a lock, but then there is a GC pause and the TTL expires. Now server B acquires the lock. So meanwhile, node A or server A is resuming. So this is catastrophic, right? Two servers now believe they own the lock, because server A will not know that the lock has expired because it went into a pause state. So now there are two writers or two servers which are believing that they own the lock. So this is where most Redis lock implementations or centralized locking strategy break. That is where there is a red lock idea, which is a quorum based lock. So instead of trusting one Redis, we are saying we trust the majority. And majority also in terms of quorum. So if you have 5 nodes, if 3 out of those 5 nodes tell that you have acquired the lock, you will consider it as successful. So this is improving single point of failure. It's actually improving fault tolerance, and it's also handling the node failure. It does improve safety, it does bring the high availability factor into consideration, but at the same point of time, it doesn't help in the eliminate the stale writers. So what is the next strategy? Next strategy is the coordination service-based locking, which most of the coordination services uses, like ZooKeeper or ATCD or Console, right? They're specifically built for coordination, as you know. So, and they will use consensus algorithm. We can have a separate video on these consensus algorithms because it will be too difficult to cover them in this video. So this one is guaranteeing more this one is guaranteeing more assurity in terms of the lock has been acquired than Redis. In this case, there are sequential nodes. Each client creates a sequential node. The smallest number owns the lock. When it disappears, next one gets it. So there is a automatic lock elimination because the node is removed. So this is deterministic and safe. So there is an automatic cleanup. There won't be a stale lock ownership, because if the client dies, then the node is automatically removed. Now, when to use, as I explained, that this is basically used where the critical coordination plays a role, and these are the systems which ZooKeeper or Kafka or Hadoop uses them, right? And then again, there is ephemeral session-based locking. This is an extension of coordinator-based locking. Here, instead of having a TTL-based locking or having a lock tied to a complete node, it is tied to a session. So if client disconnects, lock is automatically removed, and this basically prevents or eliminates the permanent stale locks. Okay. Now here, lock ownership, we need to be very conscious or careful about the understanding that what we mean by the stale lock holders versus what we mean by the correctness. They are two different problems. So this is the key insight, right? Here, as again, that because it's not TTL dependent, the session liveness is determining the ownership, and it's much safer than the time-based expiry. Now, what is a stale lock problem basically? Stale lock problem, we know, which is where most production systems are breaking. So till now, whatever strategies we discussed, they are just ensuring that the lock ownership is guaranteed, but they're still not really helping in terms of stale locks. So correctness is one of the factors which can still fail. Like node A acquires lock, node A pauses, lock expires, or the node eliminates. Then the node B acquires lock, and by any chance if node A resumes, you will have two servers assuming that they have the lock. So this is how the corruption happens. That is why there are fencing tokens, which is an advanced strategy. Here in this case, this is actually solving the stale write problem. Here, every time a lock is granted, we issue a strictly increasing number. So first lock is given a token 100, next lock will be given token 101. So it's a monotonically increasing token. This is called a fencing token. So DB will always check token has to be greater than equal to the last seen token. So in this case, the database must reject stale writes, because if a process with token 5 writes after token 6, reject it. This guarantees correctness even if locks fail. So this is production grade distributed locking. So as I mentioned, that this is ensuring that you don't have a stale locks. Systems like ZooKeeper and etcd also uses fencing token, and there are many cloud control planes also which use this technique. Now, in majority of the scenarios, we should avoid locks, because the best distributed lock strategy is often no lock at all. One of the strategies could be the partitioning, so that all operations for a key go to the same partition and there is a single writer per partition. So there is no coordination required. Another strategy could be that you allow duplicates but handle idempotency well, so that your writes are safe. So real world decision is, if your correctness is critical, then you use fencing tokens. But at the same point of time, if your workload is simple, then you use a centralized locking strategy by ensuring the high availability as well with quorum or consensus based algorithm. But if high throughput is required, then try to go for the lock free design. Hope you found this helpful. And I will make a deep dive on Redlock versus ZooKeeper in the next one. Also share few real production outages which have been caused by incorrect distributed locks. So if you like this video, please remember to subscribe and drop your comments as well if you have any feedback. Hope you have learned something today, and have a nice day. Thank you.